Okay, so let's continue where we were. We have derived the Markov chain, the solution for steady state, and the time-dependent problem. Now let's discuss what is the meaning of the mean time to threshold. So now we want to compute what is the first time, the number of MS molecule. Now everything is closed. We will see, I hope, maybe today or the next time. So the next time will be about this, and probably I will start next time polymer models about looping. But so we will see if we can finish today this. So now this is the second part, which is part 2, mean time to threshold. So let's say we start with 0 binding, 1 binding, and this is K1, K1, or let's say lambda, K minus 1, and so on, 2, 3, and if we want to go up to the end, we go, let's say, to S bound, then let's say the total number, as we've seen here. But the idea now is to say, I want to stop the process. I'm interested in the time it takes to arrive to T, the threshold T, that is the number of MS molecules equals T. So how do you write the time to arrive to this guy? Well, you have to modify the physical process, saying that this is lambda, but when you arrive to this state, are you allowed to go back? The answer is no, because you've reached the threshold. So you have to modify the physical process, and instead of having a rate to go back, now we are going to put here a rate which is 0. So this becomes an absorbing state. It is you start from here, you do whatever you do, and then when you arrive here, that's it, you are done. So this is what we want to calculate. Okay, so now let's write it slowly. So the probability to have reached the threshold before time t, which is really the distribution. So we're interested in this quantity because we would like to calculate tau, the mean time. I mean, let's define tau t, which is, again, we define it again. This is the first time that ms equals t, condition that we started at 0. ms at 0 equals 0. There's nothing, no binding. And we are interested in the mean. What is the mean? The mean is exactly the integral. Okay, I will write it in the classical way. This is t. This is the first moment of the probability distribution function, which is the derivative of this, right? Which is ddt. If you differentiate, this is the probability that tau t is less than t. And I'm stepping one step, which is you have to integrate this by parts. You integrate this and you differentiate this. And so you get that this is equal to the integral from 0 to infinity, because the term that is fully integrated is going to disappear. And this is equal to the probability that tau t is larger than t. And you have to integrate dt. And so this is exactly, okay, so now we have to understand that this can be written, the probability, so the derivative of this, which is the probability that tau t equals t, this is exactly the probability that the number of molecules equals t at time t. And actually, the derivative is exactly the derivative that you have here. So this is exactly equal to the integral from 0 to infinity of 1 minus probability that tau t is less than t, which is this pt, pt, t, probability of this is 1 minus the opposite. So this is pt of t, delta t. Okay, and now let's look at this. Now we are going to write down a Markov chain that goes from 0 to t, because we don't care about what happened here. So all of these equations are not going to be changed. They are the same, except that we need to write what happened for this guy at the state t. And now instead of having a normalization condition like this, what are we going to do with the normalization? We go from k equals 0. Instead of s here, we stop at t of pk, t equals 1. Which means that this is going to be equal, now 1 minus pt, 1 is here, minus pt, I will put it in here, and I'm left with the sum to t minus 1. So this is the sum from 0 to t minus 1 of a quantity that I will call ak. The ak is just the integral from 0 to infinity of tk t dt. So, what have we done here? This equal to this equal to this equal to this equal to, yeah. So this is the mean first passage time that we're interested in calculating. So now how do you calculate this? You have to calculate the integral of pk of t. So let's go back to here and let's integrate everything from 0 to infinity. I have a linear system. Nothing is time dependent. If things becomes time dependent, this is much more difficult. But since everything this is time independent, you just integrate everything from 0 to infinity, and now we have to write the boundary conditions both in time, in the boundary conditions for this. All right, so what happened at time 0? At time 0, no particles, no sides are bound. What does it mean? It means that the probability at time 0 to be in state k, this is 0 except when k equals 0. So this is delta k0. This is 1. Now let's write down all the when, so the first equation is valid. This one is okay, doesn't change. This one is okay up to where? Well, if you plug in here, let's say t. T we have already here t plus 1, which is not good. If we go to t minus 1, t minus 1, t minus 1, we get t, which is already something that we want to explore. So this should be true if k equals t minus 2. So this is true, doesn't change. So we have the equation, I'm not going to write it down. pk equals, this is exactly the same here, for k between 1 and t minus 2. Now let's discuss what is pk of t minus 1 and what is equal to pk of t. All right, so let's see now what happened for t minus 1. T minus 1, we're here. So when you're in t minus 1, you can come from t minus 2, from here, and you can leave here. So this doesn't affect anything. And the only possibility when you are in this position is to go here. There is no return. So we need to write this down and to modify this, what happened at t minus 1. So t minus 1 is going to be unchanged for the term that is pk. So this is p t minus 1. So we have pt minus 1. I will write it in a second what we need here. You can come from pt minus 2, but you cannot come back from pt. So this term here, which is t, this is 0, because there is no return. All right, so now let's write what is pt minus 2. This should be the rate. So this should be the rate, pt minus 2. So this is lambda. We can write the rate. Okay, let's write it the m. So this is lambda m k equals t minus 1. So if k equals t minus 1, so this is minus t minus 1, t minus 1 plus 1. And then we are s minus t minus 1. This is t plus 2. This is root m t plus 2. All right, so this is this term here. Another term in t minus 1. This is going to give us t minus 1, k minus 1, plus the term in lambda of m minus k. So this is m minus t plus 1 multiplied by s minus t plus 1. So this is what we have here and what we have in here. Okay. Now what happened when we're here? When we arrive here, so this is like the end term, except that you cannot detach here because there is no return rate. So when we have to replace the S0, which was when everything was filled, that this term does not exist because when you are here, you cannot return. There is not the probability when nothing happened here because you are dead. So this is exactly 0. And we are left with a term which is like a flux, which is lambda m minus t m minus t plus 1. T minus 1. This is the equations. For k, these equations are the same. I'm not writing them. For 0, we have this one. And this is the new boundary conditions. This is what we are interested in calculating. So we're not exactly interested in calculating this pt. If we want to calculate mean first passage time, we have to calculate the integral of them. Integral from 0 to infinity of pk of t delta t. Which means this is not that difficult. We just have to integrate this from 0 to infinity. So let's integrate everything from 0 to infinity, and then let's derive the set of equations that we need. So for this, again, I'm doing this calculation because ultimately what we're going to get from all of this is the exact dependency with respect to all the parameters. And which is exactly what we were looking for when we discussed about having for the induction of plasticity, how this can be obtained as a function of the geometry in the different parameters. All right. So let's integrate. We're integrating now. System. Integrating. System star. Let's call it star. And let's call it modified star. This is star plus these conditions. So if we integrate the first one, what do we get? Well, this is, you integrate from 0 to infinity, so this is already the derivative of something, so this is p0 of infinity minus p0 of 0 equals minus lambda ms plus k minus 1 p1, not p1. We called everything a. A is the integral by definition. So this is a0 plus k minus 1, a1. Now what is p0 of 0? By definition, at time 0, we said that all the particles are not attached. So this is exactly 1 because they are all detached. So this is correct? Yeah. So this is exactly 1. And at infinity, the probability that you find them in state 0 is 0 because ultimately you are going to escape because wherever you start, this is an absorbing state. So this is exactly 0. And now we have the first equation, which is minus 1 equals minus lambda ms a0 plus k minus 1 a1. So we're going to derive basically a matrix equation. So now this is the same. We can integrate from 0 to infinity this. So at 0, all of them were 0 because this is not in this, there was no binding at time 0. And at infinity, this is 0 because, again, the only absorbing state is 0. So this is going to be 0. And this will give us a matrix. So let's write, I'm going to write the rate instead of writing all the time this guy. I will call this rate, this rate here, we'll call it lambda k minus 1. This is how I will call the rate, and then we will give an explicit, come back to the explicit expressions. Right, so we get 0 equals, so we have the rate, so this is minus lambda so we have minus lambda k plus k minus 1 k, ak plus lambda k minus 1, ak minus 1 plus k minus 1, k plus 1, ak plus 1. So this is just what we've written here. Now we have to integrate these two guys from 0 to infinity. So from 0 to infinity, this guy will give the same 0. So this is now lambda t minus 1 plus k minus 1 t minus 1 a t minus 1, and then we are only left with lambda t minus 2 a t minus 2, and this one does not exist because it is absorbing. And now we integrate this from 0 to infinity. At infinity, by definition, the probability to find the particle at time t is exactly 1. At time 0, this is 0 because there was no particle bound. So this is 1 minus 0. We integrate this from 0 to infinity. And this is lambda lambda, let's call it lambda t minus 1, a t minus 1. So we have here a matrix that we can put in the format of a matrix. For a0, a1, at minus 1, so we have t terms, and this is exactly what we need. The sum of this guy will give us the mean first passage time. And what can be shown, and this is just an induction formula, is that you can, so basically what is the idea? Here you can solve. Lambda t minus 1 is known, so you derive, you put this in the denominator, and you have at minus 1 equal 1 divided by this. So you know at minus 1. If you know at minus 1, you plug that in here, you know at minus 2. And so you can continue from the arrival, so you go back in time, back in the process, to go to the first A0, which is going to be unknown. And in the process of doing this, you can show that the AK minus, there is a formula, which is AK minus 1 equals 1 divided by lambda k minus 1 plus k minus 1 divided by lambda k minus 1. Sorry, this is k minus 1, like the backward binding rate, multiplied by k, multiplied by ak. So, from this, you can sum all of the AK, and you end up with the, so let's, now, if we know what happened here, you use this formula, so I'm going to discuss the result now. So the result, what are the results? Suppose k minus 1 is 0, which means this is the case of irreversibility, that you can only jump from one to another. Then clearly the time tau of which is called irreversible, this is called the irreversible case. Then tau irreversible is going to be the sum from 0 to t minus 1 of ak. When k minus 1 is 0, this is 0, and you are left with the sum, which is clearly well known, of the lambda k from 0 to t minus 1. And now let's write that lambda k is what we said. This is 1 over lambda, sum of m0 minus k, s0 minus k, from 0 to t minus 1. I'm giving this example. This is well known. I mean, we did more than this in here. We are going to see what happens when k minus 1 is not 0. But now let's calculate. This will give us now the asymptotics in the different regime for this case. So what happened when basically this is the last arrival time. This is, you have to wait that the last particle arrived, and then you activate. So this is like a last the last first passage time. The last time you have to wait for the last particle to arrive to the binding site for your process to end. And so this is interesting because then this tau irreversible can be written as 1 divided by lambda m0 log of S0 divided by S0 minus t, and this is for M0 much bigger than S0 and t. T is the threshold. Obviously, you have a sum that you want to approximate here using sum of 1 over k. And we know that it is log. This is a classical result done by Euler a couple of hundred years ago. This is like log of n plus O of 1, a constant, which is the Euler constant. So you use this, and this gives us that the last arrival time basically depends on the log of the total number of particles, I mean this way, and lambda is the arrival rate. Of course, this is symmetric. If S0 is replaced by M0, you get lambda S0 plus log of M0 divided by M0 minus t, the threshold. This is for S0, much bigger than M0 and t. And M0 here, of course, the threshold is less than m0. And what is interesting, when they are equals, then it becomes t divided by lambda m0 s0. This is when m0 equals of m0 of the order of s0 much bigger than threshold. Okay, so now, so already we can see, which is what we're interested in. We didn't have to do all of this to calculate this, because this can be just seen when you have a Markov chain with just a forward rate. We knew that the mean first passage time to threshold was just equal to this, but this starts to give us the dependency in terms of the geometry, which is hidden in lambda, threshold, numbers of molecules. Now let's go to the irreversible case. When it is irreversible, that is when reversible case, which means k minus 1 not equal to 0. And then there is a full expression, which I'm not going to derive here, just give it to you. Again, this can be found by induction. So tau, mean first passage time, which is the sum of the AK, is equals to 1 over lambda, the sum from j equals 0 to t minus 1 of factorial of k minus 1 divided by lambda, which is basically the equilibrium constant to power j, sum for j for k equals j to t minus 1, factorial k minus j, m0 minus k minus 1 m0 minus k minus 1 factorial, s0 minus k minus 1 factorial divided by m0 minus k plus j factorial, s0 minus k plus j factorial. Let me check that this is okay. J going from 0 to threshold. This is the ratio to power j. K goes from j t minus 1 factorial k minus j. Yeah. All right. So how do you find this? You use this formula, and you do by induction. You have to. So you can, for example, expand in k minus 1 divided by lambda. The lambda k minus 1 is related to lambda because this is proportional to lambda. So here you can see the expansion here if you think that this is a small parameter. All right. So now let's discuss. Let's do this expansion that I just mentioned. Suppose this parameter is small. It's almost irreversible, right? Because k minus 1 is very small. So you have almost no return, but still you have something. So if we look at an expansion, really a Taylor expansion, in the variable k minus 1 divided by lambda. So this is a Taylor expansion. So this is tau t equals tau irreversible for j equals 0, and plus the linear term, and this can be written here, k minus 1 am I missing the lambda? No, okay. K minus 1 plus the sum from k equals 1 to t minus 1, lambda k minus 1. So lambda k here contains lambda. K minus 1 plus, for example, if we go to order 2, we have the term plus k minus 1 squared. Sum for k equals 1 to t minus 1, k minus 1, lambda k minus 1, lambda k minus 1, lambda k minus 2, plus the term of order 3 in k minus 1 squared. Okay, yeah, k minus cubed. In principle, this is a parameter, but lambda is contained here, so this is really the parameter of the important parameter. Okay, so now what is interesting is to obtain from this the dependency with respect to the threshold. So now this becomes more tricky. You can see that now you can, for example, put that in a computer and see this, some expansion. But what is interesting is in some limit, we can see exactly the dependency. And this came as a surprise, the nonlinearity with respect to the threshold. I mean, obviously, this is the last passage time problem. You could see from the irreversible case that you have some kind of behavior here. So, tau t, so again, there are going to be different limits. Tau t equals basically tau irreversible. So let's go in the case m0 much bigger than s0 and t, which is the similar to this one. So this means much bigger than this and t. This m0 is much bigger than these two terms. Then what you get is k minus 1 divided by lambda m0 squared, and then you see t s0 minus t minus log of 1 plus t divided by s0 minus t. Plus terms that are negligible compared to this guy. If m0 and s0 you change this, you just replace here m0 by s0. So we have the symmetrical case. I mean, I'm not writing it here. When you exchange m0 by s0, you're just replacing this formula s0 by m0. But what is interesting is s0 equals m0, much bigger than t. Then this is tau irreversible plus k minus 1 divided by 2 lambda squared, t divided by m0 squared to power cube. All of this is why this is interesting, because it gives us the dependency with respect to the threshold, this nonlinearity that are hidden here. And so I mean, this is published, I'll show you the graph. I mean, I'll draw the graph that is in here in this figure. So now if you plot tau, the mean first passage time, as a function of the threshold, again, this is in papers, but let me show you the graph. So basically the graph looks like this. As a function of t, the mean first passage time is a nonlinear function. T, and this is tau, and of course here we have fixed. So this is when s0 equals 15, m0 equals 10, we have a diffusion coefficient d. This is hidden in lambda, and you can see that you have something like this. It is, you have between, let's say, when you go to 10 here, compare when we go to 5, let's say this is 5, and this is 10. For 5, the mean first passage time was about 5, whatever units it is, this is in time. But when it is 10, the mean first passage time was about 25. Right, you multiply by 2, and this is multiplied by 5. So there is this nonlinearity which tell us something about the threshold property, the fact that if you want to wait that you have a certain number of molecules, and these molecules have to bind to a certain quantity of species, if the threshold to activation is a given number, you can see the effect of changing this threshold, what's going to be the effect. And of course, you can also study what is the effect of changing the number of molecules. This is the approach, which is usually not much pursued, but I think this is interesting because, again, it gives the dependency with respect to the different parameters, which usually you explore through the simulation. But if you have a formula, it's much nicer because you see the exact dependency and you compare with simulations. That's why it is important. All right, so this is the mean first passage time to threshold. Let's spend 5 more minutes. I want now to explain the next stage. The next stage is, you would say, all right, this is for what we've discussed, let's say, a system which is closed. But most of the systems in biology are not closed. They are transient. Something is coming, something happened, you want to look how many binding sites have been occupied, and then the process is finished. And now you ask, all right, what is in average the number of sites that has been occupied? What's the probability that during this event, the threshold has been reached? So this becomes then not a one-dimensional Markov chain, which we have seen, how to go from the different states. I've erased it, but it was on the board here. We had how to go from 0 binding, 1 binding, 2 bindings, but to a 2-dimensional Markov chain. And this becomes more tricky because we have to see how we move now in 2 dimensions.